Okay, hi and welcome to Notes 5.3. Today we're going to talk about function rules, tables, and graphs. Really, we're going to focus on the connection between them, how they're really all the same thing in just different ways that we represent them. So let's go ahead and get right into it so that we can make this video as short as possible. So we talked about what a relation was yesterday, and we said it was a coordinate point by definition. So we know it's some value of x and y, but what we didn't really do is talk about what a relation is in general. To us, it's any set of points, any set of numbers. We'll add that in, set of numbers. But particularly relation, and we said yesterday, wasn't something that we study a lot of. We do talk about it, we see them and deal with them, but we deal with more of a function. And the reason that we like the function between is that there's a specific relationship that exists there, where a relation may not have it. There may not be a very clear pattern to it. So it's a set of numbers that maybe doesn't have a definitive pattern, shall we say. So sets of numbers, but no clear pattern. And a function then would be the pattern. So where does a function get its pattern? Well, if you remember the vending machine, if I pressed A1 on the button pad, right, my input, right, my X value, if I press that in, I got out a snack, which was, I don't think it was nacho cheese Doritos, let's say, right, which would be my output and my Y value. So, and the reason I bring this up is because every domain is your X values, right? So every domain, and I know it's written backwards, that's math speak for you, but every domain has exactly one range or snack that came out of it. It could be duplicated, but every time I press A1, I better get nacho cheese Doritos. If I didn't get nacho cheese Doritos, that would make us a relation, and there was no clear pattern. So you could see how the pattern would change. This one, we have a very clear pattern. When we press a button, we know exactly what should be coming out of it. So that's kind of the main difference between a relation and a function, just to kind of summarize it. So now let's go ahead and talk about a function a little bit more specifically. So a function then, or what we'll say is function rule, we will say function more often than not. We won't actually say function rule. By definition, it's called a function rule. Is something that we can think of that's kind of like the vending machine. It actually is the vending machine in the situation. We put things into a function and out comes the snack or outputs or Y values for us. Okay? So these function rules can have three representations. Well, it is one of the representations, let's say. So a function rule is one way to represent the function. So I guess that's the difference between a function and a function rule. Functions in general, a function rule is very specific. So to make that point a little bit more clear, this would be an example of a function rule. All of the function rules are called functions, but this is a specific function rule. It can be represented in two other ways outside of this function rule. We can represent it, let me get rid of that. So it can be represented as a table, and it can be represented as a graph. Okay, so let's take a look at what that means. So if I take this function rule here, 3x plus 4, which we just saw on the other page, that is the function rule, so that's one way to represent it. But let's say I want to represent it as a table. So as a table, I get values or inputs of x or domain, and I put them into the function. So negative 2 times 3 is negative 6 plus 4 is negative 2. Out comes my output or my snack. So here's the button combination, the input, here's my output, the snack. This is the vending machine. Right? So I put things into the vending machine, snacks come out. And I can create a table of points. Okay? That's what a table represents. It's the function rule, but it's the values that go in and the values that come out of it. So the same thing, but specific to certain locations. Okay? So that's one representation of it. And of these things here, these inputs and outputs, the corresponding inputs, so negative 2 and output negative 2, they become points on a graph. Like this one here, negative 2, 2. And then if I put negative 1 in, I'm going to get 1 out of this function rule, and that point should be here. And so these points that I put into the function come together to form a graph. Okay, so the function rule makes the table makes the graph represents the function rule. The table from the table you can write the function rule, so you can go any which way between these three things. So if you're given one, you really get the other two, and those are the techniques that we're going to explore this year, how to be able to work with all three of those together. All right, so now that we know that, let's make another little thing here clear. Let me switch pages because it locked up. So I'll blow this up. let's go ahead and see what else. So a table identifies specific inputs and output values, right? Same thing we just went over. Graph gives you a visual picture, and the rule shows you what happens to the input to make the output, right? So you can see what's happening to that input. What things are we applying to it? Multiplication, division, and why it comes out as that particular output. So it says, if this is a key point, I actually should pause here for a second. It says, if you know or pick. So a lot of problems will give you a function rule and then ask you to evaluate it, which means that you put in the value and you find out what comes out. But sometimes you have to pick those. If you're given a function rule like this one here, y equals 3x plus 4, and they say graph it, they're not going to give you values to put into it. So you have to know what values you want to pick to put in. Are there right or wrong ones? No, they're all right. Any value you want to put in for x is fine. Are there ones that we use more than others? Sure, that's true. But you got to remember very specifically that you have to pick them sometimes. And they don't tell you which ones to do. And a lot of kids have a hard time with that. And they say, oh, I've got a function. What do I do with it? Well, pick any value you want and plug it in. Okay? So, and that's what we refer to as evaluate. All right, so let's go down here and get a little bit more of definitions based off of inputs and outputs. Okay, so we already know that an input is an x value. I think I hinted at the fact that it's considered an independent variable. And we'll go into that a little bit more. But independent variables are the ones that are just going to exist. So a lot of things, a lot of times that we've dealt with so far is it's time. Sometimes it's distance, sometimes it's money. These change, and it changes based off of the situation. Okay, so these will change based off the situation. But one of these variables will be controlling the other one, let's say, and that's the independent variable. The independent variable controls the dependent variable. We already know them as outputs. We know that they're on the horizontal axis, right? So the x-axis is where these would exist on a graph, right? They're always going to be found this way. These will always be your inputs, never the y value. Okay? And again, given or picked, that's the cue. Make sure that you remember that you get to pick them. All right, so the outputs then, kind of the same thing, but they're the dependent variable, so they're controlled by the independent variable. So in our distance versus time graphs, time was the controlling factor. Time marches on always, and so we could look at the distance based off the time, right? And so the time controlled how far away they existed, or how far whatever we were looking at was away. So the dependent variable is controlled by the other one. That's what dependent means, okay? So y values, we know that. We know that they're outputs. We know that they're going to be on the vertical axis, right? Our outputs, our y values, our dependent variables are on our y-axis. Okay. Okay, so we said that they're on the y-axis, but they're also evaluated for. So notice the difference there. I just want to highlight that. Given or picked for inputs, but evaluated for outputs. So you never just are really given outputs. There are some situations we'll talk about, but generally we're going to find out what they happen to be. Again, things like height, products, results, these are examples of what you'd find for an output. So moving on here, let's do some notes here to kind of fill in some of our gaps. So a function can be written as a table graph or function rule. Right here's that example we were using before, 3x plus 4. With this form of it is commonly used for graphing, which what I'm speaking of specifically is the y value, because we're about to introduce another concept here, which is what we call function notation. So this is for graphing. Okay. Function notation is for evaluating. So that's what you see here, function notation. Now this might be new to you. Most of you might not have seen it, but function notation sometimes throws a curveball to everyone. It looks like this. It's a big old f of x. It's the same thing as y. I'm going to write y equals f of x because they represent the same thing. It's the output variable. It's the dependent variable. They're the same. But sometimes we start and use y, especially for graphing. We can use it for evaluating, but f of x is especially good for, oh, you can see I wrote it right here, especially good for evaluating. Why is it good for evaluating? Because it's kind of like a window, okay? That's what I want you to know about it. It's like a window. And what's the window show us? It lets us see what we put into the function. That's going to make more sense when I do this first example too down here. All right, so this is how it's read before we do the first example. It says you read this term, f of x is how we say it. F is a function of x is another way to say it. So you can say f of x or f is a function of x. I know that sounds crazy. You can also have g of x or h of x, any value of x, okay? So going down here, let's take a look. You'll notice that this function, I'm going to write it on top, ready? Y equals x minus 6. Those are identical. They're the same thing. This would be something we'd use for graphing. You'll notice that your graphing calculator wants the input as y equals when you go to type it into your graphing calculator, or if you put it into a Desmos that we graph with, it'll have a y equals. Okay, so they're the same thing. But f of x, it wants us to evaluate right now this function. Remember, evaluate means plug a number in, get a number out. I'll pull this up over here. What does it mean to evaluate? Write this down, memorize this, know it. This is what evaluate means, because we're going to have the word solve in a little bit. And what that means to do is something else, not the same. They are not equal. Evaluate and solve are not the same thing. Okay, so evaluate clearly means plug a number in and get a number out. Okay, so that's what we're doing. So looking at this, we're going to plug this number in. We're going to substitute, if you will. I like to say plug in more than I say substitute. So we're going to take x wherever we see it in this function, and we're going to plug in a 2. So here's where the function rule comes into play. I'm putting 2 here, but guess what? I'm not going to do anything with this. I'm going to treat it just like I would treat the y. With the y, it tells me that I have y equals when I'm done. I don't do anything with the y. I don't take this 2 out. I don't divide the 2 out. I don't subtract the 2 out. I leave it like that. It's a window. What the window is telling me is that I plug 2 into the function. That's all it's there for to tell me. So here's where the part would go. So right here I'd put 2 minus 6, and we know that that's equal to negative 4. That's pretty easy. So if I plug in the input 2, the domain of 2, I get out negative 4. My output or my dependent variable, my y value is negative 4. So I get the point, ready, 2, negative 4. Notice how I didn't do anything with the f of 2. It would look the same if I did it with the y up here. Let me change my color. Change it to orange. So if I did this, it'd be y equals 2 minus 6, and then I would have y equals negative 4. So the only difference is this one would be f of 2 equals negative 4. Well, look at that. Look at the difference between those. Let me change my color again. This one, you don't know what you plugged in if you see this result here, right? You don't know what value went in to make negative 4. Well, you can follow your work, but if I'm looking at this part directly, I cannot tell. Over here, look, it's very clear that I plugged 2 in and I got out negative 4. That's what a function rule is, or a function notation. That's what a function notation is. That's quite literally it. So let's look at this one just real quick to kind of talk about it. So we've got the function of x is equal to x squared minus 4. So it's saying here is your function rule. So it wants to plug 2 in. Here's me plugging 2 into the function. So and then I plug 2 into the actual function rule. So 2 squared is 4. 4 minus 4 is 0. So in function notation, this would look like f of 2 equals 0. I would know what my point would be right away. See, it's 2 and 0. Look, it's 2 and 0. That's the benefit of the function notation. All right, so let's go down here and talk about these examples. I thought I erased that. I guess not. So right here, I erased the first one. This one says evaluate the function, right, f of a, which is equal to negative 3a plus 5. It says evaluate it to find the range for the domain. That's crazy talk or confusing talk to say, here are your x values, plug them in. That's what that means. When they say, here's a given domain, find the range, it's saying, plug in the x values, find the range. Here is 2 of them. I left up 1 and 4, but let's do 1 together. So we'll do negative 3 together. So I'm going to use function notation. So f of 3 is what I'm plugging into my function. And I'm going to now exchange that wherever I see an a. So it's going to be negative 3 times 3. That's what the a value is equal to, right? Or negative 3. So negative 3, right? I'm plugging negative 3 in. Let me make that change there. Plus 5. So negative 3 times 3 is 9. 9 plus 5 is 14. So what I got in is if I plug in negative 3, I get out 14. How come I got negative 7? Oh, there it is, 14, sorry. So when it says it wants to know the range, we talked a little bit about this the day before. We say R, colon, use our fancy brackets like this, and then we list all of the ranges, right? That's what the range is. What are all the outputs is really what the range is. Where are the outputs for this function? Well, for these 3 inputs, for these 3 domains, these 3 x values, these are the outputs, okay? And so you would list them in a set notation like that. These are all similar. This is another example. You're welcome to look. It's the exact same thing. We're plugging in. This time, find the range by using these domains. We're just using different function rules. So we would plug those in. I didn't show the work on those, but there's the solutions for it. So getting down to the last bit here, let's go ahead and put all of this together in one form. So this is going to be us taking a function rule, right? And then we're going to change it into a table by evaluation, right? We're going to use evaluation to find that. And then we're going to take that table and we're going to get points out of it, right? We're going to get an XY table that's going to get points, and then we're going to plot the points, and that's going to make the graph. So you can see we're going to go through one way of all three forms. So let's go ahead and scoot over here. Here is, well, let me rewrite the function rule right now. So it's 1/2 x plus 3. Yep, 1/2 x plus 3. So I'm going to write my function rule somewhere down over here. 1/2 x plus 3. There's my rule, right? So I'm going to input things to x, and I'm going to get out what the y is equal to. So I get to pick any values of x. Well, let's scroll back over. Sorry, I keep going back and forth. Which values are easy to use for x? Probably ones that don't make big numbers and that are close to the origin, but that's a very general rule. Usually I start with things that are close to the origin, unless I know that my function rule is going to make a graph somewhere way off, somewhere that's really large. Okay, so, but I'm pretty sure that this one's going to be near the origin, so I might use values like -2, -1, 0, 1, 2. Those would be commonly used. Okay, so now I'm going to evaluate. I picked these numbers. I picked. Okay, I chose. You have to be able to know that you have to do that. I'm going to plug them in. I'm going to evaluate them. So I'm going to do a little work here, right? So I'm going to take 1/2, and I'm going to plug in -2 plus 3. So 1/2 times -2 is -1, right? And -1 plus 3 is 2. So I put in -2, I get positive 2 out. Let's put in -1 now. I'm going to put -1 in. 1/2 times -1 plus 3. So -1 times 1/2 is -1/2. So basically I'm subtracting 1/2 from 3. So that's 2.5 then is what it goes to. So if I plug in -1, I get 2.5. So let's plug in 0. So 1/2 times 0 plus 3. So that's going to turn to 0. Now I get 3. And you can kind of see the pattern that's coming out of here, right? It's a very clear pattern. Plus 5, or plus 0.5, plus 0.5. And that's going to continue. And I actually can predict that that pattern is going to continue. And I could finish that off, but I'm not. So what I'm going to do is I'm going to start with my first point, which is -2, 2, and I'm going to go up by 1/2 each time. So here's -2, here's 2, and I'm going to go up by 1/2 for every value that I moved, right? So my next one would be -1 and up 2.5. So -1 up 2.5. And then my next point would go up another 1/2. And I would go up another 1/2. And I would go up another 1/2. And what I should get is a line that I can draw. Let me switch my color. So I'm going to get a line that I can draw through there. And I missed, but you get the idea. And you can see another example here. So that's working with all three parts. What we did is went through function notation. We went through understanding what a function rule is and the difference between that and a relation, and how to graph using it, using a table. All right, good job. We'll see you in class.